Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be sending our attention upwards, not into the night sky, but to something much closer to home. Clouds may seem like the soft and ordinary objects we're familiar with, but in reality, they are vast structures of complex physics, miraculous bodies of water, light, motion, and energy, always forming, shifting, and vanishing above our heads. Some are larger than mountains, while others are so small they could fit inside a jar. Some glow after sunset, and others unleash lightning, hail, and rain. They can emerge from forests and oceans, and even dry deserts and man-made cities. They shape the climate, our landscapes, and all the creatures that live within. And on distant worlds, clouds are stranger still, made from acid, methane, or materials far hotter than anything on Earth. The more closely we look, the more extraordinary they become. They are signs of hidden air currents, changing temperatures, and water on the move throughout the world. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your shoulders soften, let your breathing slow, and let your thoughts drift as we explore these fascinating objects together. Let's begin. Clouds may look light and fluffy, yet they can weigh a staggering 1 million pounds and still float in the air. That sounds impossible, until you remember what floating really means. A cloud is not a solid block hanging in the air. It is a vast region filled with countless tiny droplets or ice crystals spread across an enormous volume. A large cumulus cloud can contain hundreds of tons of water, yet each droplet is so small that it falls only very slowly. At the same time, the air inside and beneath the cloud is rising. Warm air from the ground keeps lifting moisture upward, which helps support the whole structure. In that sense, a cloud floats for the same reason dust can hang in a sunbeam, except on a colossal scale. The astonishing part is the contrast. What looks soft and almost weightless from below may hold as much water as a fleet of heavy trucks. The sky can seem delicate while carrying something massive above your head. Every cloud you see is built from countless invisible seeds. Water vapor does not usually turn into droplets all by itself. It needs a surface, something tiny for moisture to cling to as the air cools. That is where the hidden seeds come in. They are microscopic particles drifting through the atmosphere, made from dust, sea salt, smoke, ash, pollution, and even bits of living material. Around each one, water begins to gather. Then more gathers. Soon a droplet is born, and multiplied by billions, a cloud appears. This means that every cloud is partly a story about the world below it. Winds sweep salt up from the sea. Deserts send dust across continents. Fires loft smoke high into the sky. Volcanoes scatter ash. Even forests release particles that help shape the air above them. A cloud may look pure and simple, but it begins with debris, fragments, and specks so small that the whole sky depends on what we never see. Some clouds form so high, they glow after sunset has faded. Most clouds darken when the sun sinks below the horizon, but the highest ones can keep shining long after the land below has entered evening. That is because they are still high enough to catch sunlight from beyond the curve of the Earth. Thin ice clouds such as Cirrus often blaze gold, pink, or silver at that hour, while everything beneath them grows dim. On rarer occasions, even stranger sights appear. Noctilucent clouds form far higher still, near the edge of space, in air so thin and cold that tiny ice crystals can gather there. these clouds glow electric blue in deep twilight and seem almost unreal, as if night itself has started to shine. Their light is a reminder that sunset is not one moment, but a layered event, different at different heights. While you stand in shadow, part of the atmosphere may still be holding the last light of day. A cloud is the sky turning water vapor into something visible. Air can hold water in an invisible form, and most of the time it does. You walk through moisture constantly, without seeing it at all. Then conditions change. Warm air rises, or cooler air moves in, and the temperature drops to the point where the invisible vapor can no longer stay hidden. It gathers into droplets or ice crystals, and suddenly the sky reveals what was there all along. That transformation is one of the most ordinary miracles in nature. A clear day becomes textured. Empty blue becomes shape, depth, brightness, shadow. You are watching a boundary appear between what the eye can detect and what it cannot. In a way, clouds make the atmosphere visible. They trace the movement of moisture, temperature, and motion in real time. Without them, the air above us would be far harder to imagine. With them, the sky becomes a living map, drawn in water and light. Thunderstorms can build clouds taller than Mount Everest in under an hour. On the right day, the atmosphere can become explosively efficient. Heat from the ground warms moist air near the surface, and that air begins to rise. As it climbs, it cools, moisture condenses, and energy is released back into the storm, pushing the air even higher. What begins as an ordinary puffy cloud can rapidly become a towering thunderhead that punches upward through much of the atmosphere. Some of these giants reach heights of 10 miles or more, placing their tops above Everest and spreading outward into the familiar anvil shape. Inside, the storm is a vertical engine. Air rises, sinks, freezes, melts, collides, and charges itself with electricity. From the ground, the growth can feel almost theatrical. A bright summer sky changes by the minute. A harmless cloud becomes a mountain. Then thunder begins. Few things reveal the raw speed and power of the atmosphere more clearly than watching a storm build itself overhead. The bright white color of clouds comes from sunlight scattering through countless tiny water droplets. Clouds do not shine with their own light. Their whiteness comes from sunlight bouncing in every direction through tiny droplets and ice crystals. Because the particles in most clouds are large enough to scatter all visible colors fairly evenly, the combined light returns to your eyes as white. That is why sundered clouds can look brilliant against a blue sky. The blue itself is created by a different kind of scattering in the air, one that favors shorter wavelengths. So, in one glance, you are seeing two related optical effects shaping the entire sky. When a cloud grows thicker, less light can pass through it, and the underside turns grey. During sunrise and sunset, clouds can flare orange or red because the shorter colors have been filtered out along the longer path through the atmosphere. So a cloud's color is never random. It is a running conversation between sunlight, water, depth, and the angle from which evening or morning arrives. Some clouds make their own lightning, hail, and violent internal weather. A storm cloud is not just a place where weather happens. It is a whole weather system in itself. Inside a powerful thundercloud, fierce updrafts can hurl droplets upward, while downdrafts drag cold air and rain back down. Ice particles collide, separate, and charge one another. Water freezes, melts, and freezes again. Hailstones are built layer by layer as they are thrown repeatedly through zones of supercooled water. Lightning flashes when the electrical imbalance grows too great for the cloud to contain. In the same storm, one part may be building ice, while another is releasing heavy rain, and another is feeding a burst of wind toward the ground. From outside, you may only hear thunder and see a dark tower. Inside, it is a churning world of collisions, currents, and energy. These clouds are so dynamic that they can manufacture their own hazards while still growing, turning the sky into a self-powered engine of chaos. Earth is the only known world where clouds are made of water. Clouds exist across the solar system, but Earth's are special because they are made from the substance that shapes rivers, oceans, rain, snow, and life itself. On Venus, the clouds are built from sulfuric acid. On Titan, Saturn's largest moon, they form from methane. On Jupiter and Saturn, different chemicals condense at different heights into vast layered decks. Farther out, clouds may contain ammonia or methane ice. Some worlds beyond our solar system may even have clouds of vaporized rock or molten minerals. Earth, by contrast, has an atmosphere and temperature range that let water move through all three familiar states with remarkable ease. That gives our planet a sky tied directly to seas, lakes, glaciers, plants, and living bodies. Every cloud above you is part of the same circulating water that fills the landscape below. As far as we currently know, no other known world has that exact kind of sky woven so deeply into life. Entire landscapes depend on clouds that never become rain at all. It is easy to think clouds matter only when they break into rain, but some of the most important ones do something quieter. In coastal deserts, mountain forests, and dry island slopes, low clouds and fog can deliver moisture without any downpour. They brush across leaves, needles, moss, and rock, leaving behind droplets that drip to the ground or are absorbed directly by plants. In some cloud forests, this hidden water is essential. Trees comb moisture from the air. Ferns, orchids, and mosses thrive where rainfall alone would not be enough. In places like the Atacama Fringe or parts of the Canary Islands, fog has even been harvested with nets to collect water from the sky. These landscapes survive because clouds arrive as touch rather than storm. No thunder is needed. No dramatic rainshaft appears. The air simply grows wet enough to feed life. Sometimes the sky sustains a region by brushing past it. The shape of a cloud can reveal the hidden motion of air. Clouds are not random decorations. They are visible traces of forces that would otherwise remain completely unseen. A flat cloud base often marks the level where rising air has cooled enough for condensation to begin. A cauliflower tower shows strong upward motion. A stretched veil suggests winds are shearing the cloud apart at higher altitude. Lenticular clouds reveal air flowing in waves over mountains. Parallel bands called cloud streets show rolls of rising and sinking air lined up with the wind. Even ragged fragments racing beneath a storm can hint at turbulent inflow being pulled inward. To someone who knows what to look for, the sky becomes a kind of atmospheric handwriting. You can read stability, moisture, lift, and wind in the shapes overhead. That is part of what makes clouds so fascinating. They are beautiful, but they are also informative. The invisible atmosphere is always moving, and clouds let you watch that motion written across the sky. Fog is simply a cloud that has settled onto the ground. That idea makes an ordinary morning feel much stranger. When fog rolls across a field or drifts through a street, you are not looking at something separate from the sky above. You are standing inside the sky itself. The same process that forms clouds overhead can happen right at the surface when air cools enough for moisture to condense into tiny suspended droplets. That is why fog can swallow roads, soften lamps into halos, and make familiar places feel newly mysterious. In coastal regions, it can arrive in great sweeping banks. In valleys, it can pool overnight like pale water. In forests, it threads between trunks and leaves everything beaded with moisture. Pilots, sailors, and travelers have feared it for centuries because it erases distance so completely. Yet it is also intimate. Most clouds remain above us. Fog comes down to meet us, turning, walking, breathing, and seeing into part of the weather itself. Contrails can spread into cloud cover and reshape the whole sky. At first, they look like narrow white scratches trailing behind high aircraft, but they can become something much larger. When a jet passes through very cold, humid air, water vapor from its exhaust freezes into tiny ice crystals. If the surrounding atmosphere is dry, the line fades quickly. If it is moist enough, the trail persists, widens, and begins to drift with upper winds. Over time, one line can feather outward into a veil. Many can merge into a broad, milky layer that changes the look of the entire sky. Some light softens. Blue becomes hazy. The day takes on a thin, bright overcast that was not there before. In busy flight corridors, this transformation can happen repeatedly. What began as several distant aircraft marks turns into a human-made addition to cloud cover. It is a striking reminder that the upper atmosphere is sensitive, and that even modern travel can leave patterns written high above our heads. Some desert clouds can trigger deadly floods within a single hour. Deserts are often imagined as places where clouds barely matter, yet that is exactly what makes certain storms so dangerous. The ground is usually hard, baked, and poor at absorbing sudden water. Dry channels may sit empty for months or years, looking harmless. Then towering storm clouds build over distant hills, or over the desert itself, and release intense rain in a short, violent burst. Water races downhill with astonishing speed, gathering mud, stones, and debris as it goes. The wash that seemed lifeless becomes a torrent. Roads vanish. Cars are swept away. In slot canyons, the danger is even worse because floodwater can arrive from rain that fell far beyond sight or hearing. Blue sky overhead is no guarantee of safety. The storm may be miles away and still send destruction rushing toward you. In these landscapes, clouds can turn absence into catastrophe almost instantly, proving that dryness and flood are not opposites at all. Lenticular clouds can hover like flying saucers above mountain peaks. Few clouds look so deliberate. These smooth, stacked shapes often appear fixed in place, as if some silent object has chosen to remain above a ridge or summit. Their stillness is what makes them uncanny. While other clouds drift and change visibly, these seem to hover. They form when strong, moist air flows over mountains and begins to move in atmospheric waves, rising and sinking on the far side, much like water passing over a submerged rock. At the crests of those waves, the air cools enough for moisture to condense. As the air continues onward, droplets evaporate and reform, so the cloud stays in one position even though wind rushes straight through it. Pilots respect them because they can signal powerful turbulence nearby. Observers on the ground often mistake them for something unnatural. Yet their elegance comes directly from physics. A mountain disturbs the sky, and the sky answers with a shape so strange it looks designed. Momentous clouds hang in pouches that look almost upside down. They are among the strangest sights the atmosphere can produce. Instead of towers rising upward or sheets spreading across the sky, these clouds hang beneath a larger cloud deck in rounded lobes, as if the sky has developed a field of soft dimples. Their appearance can feel unsettling because it seems to reverse the usual logic of clouds. We expect billows to grow upward, not droop from above. Momentous often form beneath the anvils of severe thunderstorms, though they can also appear with volcanic ash or other turbulent cloud layers. Scientists link them to sinking pockets of cold, moisture-rich air and to complex mixing along the base of the cloud. What makes them so memorable is the contrast between beauty and menace. At sunset, they can glow bronze or rose and look almost sculpted, yet they often appear near storms of enormous power. It is as if the atmosphere, after building a thunderhead, signs its work with a pattern unlike anything else overhead. No two clouds are truly alike for more than a moment. That may sound poetic, but it is also physically true. A cloud is never a fixed object. It is a temporary pattern made from droplets or ice crystals that are constantly forming, evaporating, moving, and being replaced. Wind stretches one edge while sunlight thins another. Rising air builds fresh bulges. Drier air eats away at the margins. What looks steady from a distance is changing second by second. Even if two clouds appear similar, they are made from different motions, different temperatures, and different histories of moisture. This makes the sky one of the most dynamic things we ever look at, yet we often treat it as background scenery. If you watch a single cloud carefully for just a few minutes, you can see it becoming something else in real time. It swells, fades, breaks, reconnects, or vanishes. The atmosphere never pauses long enough to make an exact duplicate. Every cloud is a brief event, not a lasting thing. A cloud begins when warm air rises and cools enough. That simple sequence is one of the great engines of the sky. Air near the surface can be warmed by sunlight, by darker ground, by cities, or by air flowing over warmer terrain. Once that air becomes buoyant enough, it starts to rise through the atmosphere. As it rises, the pressure around it decreases, so it expands. Expansion causes cooling. If the air cools to the point where it can no longer hold all its moisture as invisible vapor, condensation begins. Tiny droplets appear, and a cloud is born. That means every ordinary puffy cloud is evidence of movement. The sky is not filling up by chance. It is reacting to invisible lifting from below. This is why afternoon clouds often blossom after morning heating, and why the sky can suddenly become active after seeming empty. The moment a cloud appears, you are seeing warm air complete a journey upward, carrying hidden moisture into visibility as it goes. Tiny droplets in clouds are often smaller than a human hair. That scale helps explain why clouds can seem substantial without falling apart into instant rain. Individual cloud droplets are extraordinarily small, often only a few tens of micrometers across. A human hair is much thicker. Because each droplet is so tiny, it has very little weight and can remain suspended in moving air with remarkable ease. Billions upon billions of these droplets can gather into a visible cloud while still being too small to drop quickly to the ground. If a cloud were made of fewer, larger drops, it would rain much sooner. Instead, the sky often holds water in this almost powdered form, a floating population of microscopic beads. That is part of what makes clouds visually soft. They are built from particles so fine that light can scatter through them beautifully, while air currents keep them aloft. A towering cloud may stretch across miles, yet much of what you see is made from droplets smaller than anything you could feel individually. Ice crystals and water droplets can exist together inside one cloud. That mixed state creates some of the most important drama inside the atmosphere. In certain temperature ranges, especially in middle vol and storm clouds, liquid droplets can remain unfrozen even when the air is well below freezing. At the same time, tiny ice crystals are also present. So the cloud becomes a place where liquid water and solid ice coexist in uneasy balance. This matters because water vapor tends to settle more readily onto ice than onto liquid droplets in those conditions. The ice crystals grow, the droplets shrink, and the balance shifts. As the crystals become heavier, they may fall, gather more moisture, and change form on the way down. Snow, sleet, freezing rain, and ordinary rain can all begin with processes unfolding in this partly frozen world. A cloud may look calm from below, but within it, two phases of water are competing and transforming. That hidden coexistence helps turn suspended moisture into actual weather. Some clouds are made almost entirely of ice, not liquid water. High in the atmosphere, the air is so cold that clouds often fall not from droplets at all, but from countless tiny ice crystals. These clouds tend to look wispy, fibrous, or feathery, because crystals interact with light and wind differently from liquid droplets. Instead of the puffy texture of lower clouds, they often spread in fine streaks and delicate threads. When sunlight passes through them just right, they can create halos, sundogs, and other luminous displays around the sun or moon. Their presence also tells you something about the atmosphere above. The temperatures aloft are bitterly cold, and moisture is being organized into crystalline form rather than suspended liquid. In a sense, these are clouds made from airborne frost. They may look fragile, yet they can stretch for great distances and often arrive ahead of changing weather. To look at them is to see the upper sky writing in ice instead of water. Cirrus clouds are made of ice and live in the highest skies. They often appear as white streamers, feathers, or fine combed threads drawn across deep blue. Because they form so high, usually where the air is very cold and thin, they are built from ice crystals rather than liquid droplets. Their shapes are sculpted by strong winds aloft, which pull them into elegant streaks and curls. Seen at sunset, they can burn gold and crimson long after lower clouds have gone grey, giving them a reputation for beauty that painters and skywatchers have long loved. Yet they are not just decorative. They can signal moisture moving into the upper atmosphere and sometimes arrive ahead of larger weather systems. Their direction and pattern may hint at winds far above anything we can feel on the ground. So when you notice them stretching overhead like white brushstrokes, you are seeing the highest ordinary clouds in the sky, where water has become ice and the atmosphere reveals its upper flow. Cumulus clouds are the great rising towers of fair weather days. They are the clouds most people learn to draw as children, bright heaps with rounded tops and flatter bases, but their simplicity hides a fascinating origin. These clouds often appear on sunny days when the ground has been warmed enough to send bubbles of air upward. Each bubble rises, cools, and condenses into a growing white mass. The result is a sky full of individual towers that seem to bloom from nowhere by late morning or afternoon. Their crisp outlines and sunlit domes make them feel cheerful, almost friendly, which is why they are so closely tied to pleasant weather in the popular imagination. Yet they are also the visible fingerprints of convection, the atmosphere's vertical motion made easy to see. Watch one carefully and you can often see it building in pulses, bright cauliflower humps appearing and fading. A fair weather sky is not passive at all. It is busy with upward movement, and these clouds make that motion visible. Stratus clouds can turn an entire sky into one grey sheet. There are days when the sky seems to lose all depth and become a single continuous ceiling. That is the work of stratus. Instead of forming as separate heaps or towers, this type spreads as a broad layer that can cover vast areas with remarkable uniformity. It often develops when stable air cools gently over a wide region, allowing moisture to condense into a low blanket rather than into isolated clouds. The effect can be strangely powerful. Shadows fade. Sunlight becomes diffuse. Landscapes take on muted colors. Distance feels flatter, and time itself can seem slower under such a sky. Stratus may bring drizzle, mist, or simply a dull lid of cloud that hangs all day. Yet there is something impressive in its scale. One process in the lower atmosphere can smooth the whole dome above into a single texture. It is the cloud of overcast moods, of soft light, and of entire days wrapped in one unbroken layer. Nimbus simply means a cloud is carrying rain. The word has an old, almost mythic sound, and for good reason. It comes from a long tradition of naming clouds by what they do, as well as how they look. When nimbus appears in a cloud name, it signals that the cloud is producing precipitation. That can mean a dark layered rain cloud spreading across the sky, or it can be part of the name of a towering thunderstorm. The important point is that the cloud is no longer only suspended moisture. It has crossed into release. Water is now leaving the cloud and falling toward the ground. This makes nimbus less about shape and more about action. It marks a transition from potential to event, from sky to weather touching the land. Once you know the meaning, cloud names become easier to read. The atmosphere starts sounding almost like a language. In that language, nimbus is the word that says the cloud above has begun to empty itself. Cumulonimbus clouds are the giants behind thunder, hail, and lightning. These are the true skyscrapers of weather, towering upward with enormous vertical reach and often spreading into flat anvils near their tops. They begin with rising, warm, moist air, but under the right conditions they do not stop at a modest fair weather form. They keep growing, feeding on instability, pushing higher and higher until they become deep storm engines. Inside them, air can surge upward at astonishing speed, carrying moisture into freezing regions where ice forms, collides, and helps generate charge. That is where lightning is born. Hail can grow there too, cycling through powerful updrafts before gravity finally wins. Heavy rain, strong downdrafts, and sometimes tornado-producing rotation can all emerge from these same structures. From a distance, they may look majestic, even beautiful. Up close, they command respect. Few things make the atmosphere feel more alive than one of these giants building across the horizon, turning summer light into thunder and electric darkness. Outer cumulus clouds can hint that a storm is building later. They often appear as patches or rows of rounded cloudlets in the middle levels of the sky, smaller than low puffy clouds, and higher than the forms most people notice first. On some mornings, they are simply part of a beautiful patterned sky. On others, they are a warning that the atmosphere is becoming more interesting than it seems. Because they form in the middle atmosphere, they can reveal moisture and instability above the surface long before a storm actually breaks. If warm, humid air is rising below while these clouds are already gathering aloft, the ingredients for later development may be coming together. Some patterns, especially when towers begin to poke upward from them, have long been watched as a sign that thunder may arrive by afternoon. They are subtle compared with the drama of a thunderhead, but that is exactly what makes them fascinating. Sometimes the sky whispers before it shouts, and these clouds are part of that early whisper. Mares' tails in the sky often signal changing weather ahead. This old phrase usually refers to long, fine streaks of high cloud that trail across the sky like wisps of horsehair. They are a familiar form of cirrus, shaped by strong winds in the upper atmosphere and stretched into elegant lines. For centuries, people who lived close to the weather paid attention to them because they often arrived before larger changes. As moisture begins increasing high above, ahead of an approaching front or disturbance, these streaks can appear first, delicate and easy to overlook. Later, the sky may thicken with more extensive cloud and eventually bring rain or shifting winds. The saying survived because it captured a real pattern. The atmosphere often sends signals in sequence, and these fine icy strands can be among the earliest. They are beautiful in their own right, but they also carry a hint of what may come next. A change of weather can begin not with thunder, but with hair-like lines in blue. Shelf clouds can stretch across the horizon like a moving wall. Few cloud forms create such immediate drama. A shelf cloud usually develops along the leading edge of a thunderstorm's outflow, where cool air rushing outward from rain-cooled downdrafts undercuts warmer air ahead of the storm. That warm air is forced upward, moisture condenses rapidly, and a long, low wedge of cloud forms at the storm's front. From a distance, it can look like the storm has built an edge, dark, layered, and advancing. Light changes as it approaches. Wind often freshens. The horizon can seem to harden into a boundary between calm and turbulence. Unlike the rotating features linked more directly with tornado danger, a shelf cloud is attached to the gust front itself, a sign of the storm pushing air outward like a spreading tide. Even without a tornado, it can bring fierce straight-line winds and sudden temperature drops. It is one of the clearest ways the atmosphere shows motion as architecture, building a wall from wind and moisture. Wall clouds can spin beneath storms before tornadoes begin. Beneath certain severe thunderstorms, a lowered block of cloud can descend from the storm base and begin to draw intense attention from meteorologists and storm watchers. This is the wall cloud, often found beneath a rotating supercell. It forms where warm, moist air is being pulled strongly upward into the storm, lowering the cloud base in one concentrated area. Sometimes it hangs there dark and ominous. Sometimes it turns visibly. Not everyone produces a tornado, but many tornadoes begin in connection with one. That is why people watch them so carefully. They can be the place where a storm's hidden rotation tightens, focuses, and reaches downward. The visual effect is unforgettable because it feels as though the storm is trying to descend toward the land. The giant cloud above is no longer distant. It has formed a lowering, and that lowering may become something far more dangerous. In that moment, the sky looks concentrated, deliberate, and very alive. Roll clouds can travel as long, spinning tubes of air. They are among the most remarkable cloud forms because they can look like a giant horizontal cylinder suspended just above the land, sometimes stretching for miles. Unlike a tornado, which spins around a vertical axis, this cloud rolls along a horizontal one, as if the atmosphere has laid down a turning wheel. It often forms when cool outflow from a storm interacts with warm, moist air ahead of it, lifting and condensing moisture into a detached tubular band. The cloud itself may seem to rotate as it advances, though the whole feature is usually moving with the surrounding air as well. In rare places, such as northern Australia, spectacular examples can appear with astonishing length and definition, becoming famous enough to attract skywatchers from around the world. What makes them so captivating is their combination of motion and geometry. The sky suddenly contains a rotating line, clean and improbable, like weather transformed into an enormous moving sculpture. Cloud streets are long rows of clouds aligned by the wind. Seen from an airplane or a satellite, they can make the atmosphere look organized with almost impossible precision. Instead of random puffs scattered across the sky, you get parallel bands stretching for miles, like lanes painted across the lower atmosphere. These form when cold air moves over a warmer surface and begins to rise in rolling cylinders. In one part of each roll, air is lifting and moisture condenses into cloud. In the next part, air is sinking and the sky stays clear. The result is a repeating striped pattern written by convection and wind together. Pilots study them because the rising sections can provide lift, and glider pilots sometimes use them like aerial highways. What makes them so striking is the contrast between invisibility and order. The air itself is moving in long rotating tubes. yet you only see the sections where water reveals the pattern. The sky becomes a map of motion, clean, rhythmic, and unexpectedly geometric. Kelvin Helmholtz clouds curl like breaking waves high in the air. They look so much like ocean surf that it feels wrong to find them overhead. Along the top edge of a cloud, smooth crests begin to roll forward, each one shaped like a wave about to crash. This rare pattern forms when two layers of air are moving at different speeds, or sometimes in different directions, and the boundary between them becomes unstable. The faster layer drags across the slower one until the interface starts to curl. Moisture outlines the motion, and for a few brief moments, the sky becomes a sea. These clouds are usually short-lived because the structure quickly breaks apart into turbulence. That fleeting nature makes them even more memorable. You may glance up and see one of the most elegant demonstrations of fluid physics in nature, then watch it dissolve almost immediately. They are a reminder that the atmosphere behaves like a flowing substance at every scale, and sometimes it reveals that truth with startling beauty. Hole-punch clouds appear when ice crystals suddenly empty a cloud. They can look as if someone has taken a giant circular bite out of the sky. In a thin layer of middle-vol cloud, a crisp opening appears, often with feathery streaks falling beneath it. The process begins when part of the cloud is disturbed, and ice starts to form suddenly in air that was full of supercooled liquid droplets. Once those first crystals appear, they grow rapidly by drawing water vapor away from the surrounding droplets. The droplets evaporate, the cloud disappears in that region, and a widening hole opens up. Airplanes passing through the layer can sometimes trigger the process by creating rapid cooling around propellers or wings. The result is one of the strangest sights in weather, a bright gap surrounded by intact cloud, as though the atmosphere has quietly torn itself open. It feels almost artificial, yet it is the product of water changing state and setting off a chain reaction in midair. Full streaks can leave bright gaps that look almost impossible. What makes them so captivating is the combination of absence and motion. You may see a smooth cloud sheet with a sudden clear opening cut through it, while beneath the gap hangs a soft curtain of icy streaks descending toward the lower atmosphere. Those streaks are the clue. They show that ice crystals have formed and begun to fall out of the cloud. As they grow, they steal vapor from nearby droplets, which then evaporate, leaving a widening patch of blue or brighter sky behind. The falling crystals may drift, spread, and shimmer as they descend, producing a scene that looks more like a visual trick than weather. Sometimes the opening is round. Sometimes it stretches into an ellipse with ragged edges. Either way, it gives the strange impression that part of the cloud has been erased, while another part is still spilling downward. It is one of the clearest examples of a cloud destroying itself while remaining beautiful. Pileus clouds form like caps above fast-growing thunderheads. If you watch a powerful cloud tower rising quickly enough, you may see a smooth little hood appear above it, perched like a lid or hat. That delicate feature is a sign of intense upward motion below. The main cloud is punching into a layer of moist air and forcing it to rise so suddenly that the lifted air cools and condenses into a thin cap. For a moment, the tower seems to wear its own crown. These caps are often smooth and elegant because they form in a stable layer before turbulence tears at them. Sometimes they appear in stacks, one above another, as the storm keeps surging upward through the atmosphere. Their presence can be an early sign that the cloud beneath is growing with unusual strength and may become a formidable thunderstorm. So even though Pileus clouds look graceful and almost fragile, they are often attached to raw power. The prettiest hat in the sky can sit atop a storm that is rapidly becoming dangerous. Aspiratus clouds ripple like a stormy sea across the sky. They are among the most unsettling cloud formations because they seem to turn the whole atmosphere upside down. Instead of familiar puffs or layers, the underside of the cloud deck becomes rough, undulating, and deeply textured, like the dark surface of an ocean seen from below. Light filters through the folds in shifting patches, which makes the sky appear to move even when the cloud itself is broad and slow. This formation is still not fully understood, though it is linked to atmospheric waves, instability, and disturbed layers of air interacting in complex ways. What makes it so powerful as a sight is scale. A small, strange cloud can be charming. A spiritus can cover huge portions of the sky, making an entire afternoon feel transformed. People often describe it as apocalyptic or alien, yet it is not usually tied to the most violent weather. It is the atmosphere showing texture on a grand scale, revealing hidden turbulence as a rolling landscape overhead. Banner clouds can stream from mountain peaks like ghostly flags. From a distance, they can make a summit look as though it is smoking or flying a white pennant into the wind. These clouds form on the downwind side of a sharp peak when moist air flows over the mountain and creates a local zone of lifting and cooling. Condensation occurs just behind the summit, producing a streamer that seems attached to the mountaintop itself. The effect can be remarkably dramatic on isolated high peaks, where the cloud appears steady even while strong winds race through it. Climbers have long noticed them because they often signal fierce air movement near ridges and summits. In that sense, the mountain is not just standing in the weather. It is shaping the sky around it. The cloud becomes a visible signature of airflow interacting with rock. A peak can write on the atmosphere, and the result is a pale, trailing flag that marks where land and wind are locked in constant conversation. Cap clouds cling to summits when moist air climbs upward. They can make a mountain look crowned, as though the peak has gathered its own private piece of sky. These clouds form when humid air is forced up a slope and cools enough to condense near the summit. Because the terrain keeps lifting the air in the same place, the cloud often appears fixed over the peak, even while wind flows continuously through it. That strange steadiness is part of the appeal. The mountain seems to be wearing the cloud rather than passing beneath it. In some regions, cap clouds are taken as signs of changing weather or strong winds over the heights. For climbers and mountain communities, they can be both beautiful and practical, hinting that the upper air is active even if the valley below feels calm. They also reveal something profound about landscape and atmosphere. A mountain does not merely sit under the sky. It can shape condensation itself, pulling a cloud into existence just by standing in the way. Fractus clouds are torn scraps shaped by restless winds. They often appear beneath larger cloud decks or near storms as ragged shifting fragments with no neat boundaries and no stable form. Unlike more orderly clouds, they look broken from birth, as if the atmosphere has ripped pieces from a larger whole and left them racing through the lower air. These fragments usually form in damp, turbulent conditions, where moisture condenses into shreds that are quickly stretched, lifted, and distorted by gusts. Their motion is part of what makes them compelling. They seem nervous, temporary, and unsettled. Beneath a storm, they can scud along at surprising speed and make the sky feel more threatening than it might otherwise. People sometimes mistake them for more dangerous rotating features because they look wild and low, but their chaos often comes from turbulence rather than organized rotation. Even so, they tell an important story. The air below the main cloud is active, moist, and unstable enough to tear little clouds into being, then reshape them almost instantly. Virgo falls from clouds, then vanishes before reaching the ground. It is one of the most elegant tricks the atmosphere can perform. From the base of a cloud, pale pale streaks of precipitation descend like curtains or silver threads, yet they never arrive. Somewhere in the drier air below, the falling droplets or ice crystals evaporate or sublimate away. What you see is rain or snow in transit, visible for part of its journey and then gone. In dry regions, virga can be common and especially beautiful at sunset, when the streaks catch low light and seem to glow. But it is not only a visual wonder. As precipitation evaporates, it cools the air around it. That cooler air can begin to sink rapidly, sometimes helping create strong downdrafts or sudden gusty winds at the surface. So a cloud may appear to be withholding its rain while still changing the weather below. Virga shows that even lost precipitation matters. The atmosphere can begin an event, then erase it halfway through. Some rain begins as snow high above, then melts on the way down. That means an ordinary rainy day may start with frozen crystals in the upper sky. In many clouds, the air aloft is well below freezing, so precipitation forms first as snowflakes or ice particles. As those particles fall, they may pass into warmer layers of air. If the warm layer is deep enough, the ice melts completely and reaches the ground as rain. This hidden journey matters because the temperature structure between cloud and surface determines what finally arrives. A slight change in the depth of cold or warm air can turn the same falling particle into rain, sleet, or freezing rain. So when you feel drops on your face, you may be catching something that began its life as a snow crystal far above sight. That transformation gives rainfall a secret history. What seems simple at the ground may have crossed several worlds on the way down, changing state as it passed through invisible layers stacked through the atmosphere. Hail grows by riding powerful updrafts inside thunderclouds again and again. A hailstone is built through repetition and violence. Inside a strong storm, a small frozen pellet can be swept upward by intense rising air into regions filled with supercooled droplets. Those droplets strike the pellet and freeze onto it. If the growing stone becomes heavy enough, it starts to fall, but another surge may catch it and hurl it upward again. Each trip adds new layers. Some freeze clear, others cloudy, depending on conditions inside the storm. If you cut a large hailstone open, you can sometimes see those layers like rings in a tree, each one a record of a journey through different parts of the cloud. Eventually, the stone becomes too heavy for the updraft to support, and it plunges to the ground. So when hail hits with startling force, it is not just frozen rain. It is the finished product of repeated lofting, icing, and survival inside one of the most turbulent environments in the atmosphere. Supercooled droplets stay liquid far below water's normal freezing point. That sounds like a contradiction, yet the atmosphere does it all the time. In very clean air, tiny liquid droplets can remain unfrozen well below zero because freezing usually needs a trigger, such as a suitable particle or a disturbance that helps ice begin. Until that happens, the droplets can exist in a delicate suspended state, liquid but ready to change instantly. This hidden condition is common in many cold clouds and is one of the reasons winter weather can be so complex. The droplets look harmless because they are just water, but the moment they strike a surface or encounter an ice nucleus, they can freeze with startling speed. That makes them important in storms, in icing events, and in the internal life of cold clouds. The idea itself is astonishing. Water, in defiance of expectation, can stay liquid in air cold enough to freeze solid objects at the ground. The sky often holds unstable possibilities, waiting for one small trigger. Aircraft can accidentally freeze cloud droplets into sudden dangerous ice. To a pilot, some clouds contain a hidden hazard that cannot be judged by appearance alone. When an aircraft flies through air filled with supercooled droplets, those liquid droplets can strike the cold surfaces of wings, propellers, sensors, or the fuselage and freeze on contact. The buildup can happen fast. A thin layer of ice changes the shape of a wing, adds weight, increases drag, and can reduce lift in ways that make flying far more dangerous. Engines and instruments may also be affected. What makes this especially unnerving is that the cloud itself may not look dramatic. The danger lies in its temperature and microphysics, not necessarily in dark colors or obvious violence. Pilots therefore learn to respect certain conditions with great care. The sky can offer a trap made from invisible liquid water in freezing air. A cloud that seems soft and harmless from the ground can become an environment where metal gathers ice and performance changes in minutes. Lightning helps clouds balance enormous charges built by colliding particles. Inside a thunderstorm, the air is full of violent traffic. Ice crystals, graupel, hail, and droplets are being thrown upward and downward through different temperature zones. As these particles collide, electric charges separate. Lighter crystals often gain one kind of charge and are carried higher, while heavier particles gather another and sink lower. Over time, the cloud becomes electrically divided, with immense imbalances between different regions and often between cloud and ground as well. Lightning is the atmosphere's sudden answer to that imbalance. A conductive path forms through the air, and charge rushes along it in an intense flash. For a fraction of a second, the storm is reordering its own electricity. That is why a lightning bolt is both beautiful and violent. It is not random decoration in a storm. It is a discharge event born from countless collisions among tiny particles inside the cloud. The flash we see is the visible solution to a problem the storm created for itself. Thunder is the sound of air exploding from lightning's heat. A lightning channel becomes hotter than the surface of the sun for an instant. That extreme heating happens so quickly that the surrounding air cannot expand smoothly. Instead, it blasts outward in a shock wave. As that wave travels away and weakens, we hear it as thunder. So the rumble rolling across the sky is not the cloud growling in some vague sense. It is air responding violently to a sudden path of extraordinary heat. Close to a strike, the sound can crack like a cannon, because the shock is still sharp. Farther away, it stretches into a long rolling growl as echoes bounce off terrain, clouds, and layers of air, while different parts of the lightning path reach your ears at slightly different times. Thunder is therefore both immediate and architectural. It carries information about distance, landscape, and the shape of the bolt itself. Every rumble is the atmosphere adjusting after a brief electric furnace has ripped through it. The anvil of a storm marks where rising air hits a limit. A thundercloud can rise with astonishing force, but even that upward surge eventually reaches a layer of the atmosphere that resists further ascent. Near the top of the troposphere, the air above becomes more stable, so the storm's rising plume can no longer keep punching straight upward with the same freedom. Instead, it spreads sideways, flattening into the broad shape known as the anvil. That familiar form is therefore a sign of success and restraint at once. The storm has climbed high enough to reach a ceiling, then it spills outward along it. Seen from miles away, the anvil can look majestic, stretching across the sky like a giant shield or platform. It may cast shadow far beyond the rain below and spread ice cloud across large regions. In severe storms, parts of the updraft can still overshoot briefly above the anvil, showing exceptional strength. But the anvil itself marks the altitude where the atmosphere says, "No higher, spread here instead." A thunderstorm can contain updrafts stronger than many tornado winds. It is easy to think of a storm mainly in terms of what comes down, rain, hail, and lightning, but some of its fiercest motion is upward. In the core of a powerful thunderstorm, air can rise at tremendous speed, sometimes fast enough to keep large hailstones suspended while they grow. These updrafts are the lifting engines that build the storm's height and help separate particles, feed precipitation processes, and sustain severe weather. In the strongest supercells, the upward rush can exceed speeds that rival or surpass winds found in weaker tornadoes. That means the storm is not just a cloud dropping weather from above. It is a vertical machine capable of launching moisture and ice deep into the atmosphere with extraordinary force. We rarely feel that power directly because it is hidden inside the cloud, but its effects are everywhere in the storm's structure. A thunderhead is held up by motion fierce enough to rival some of nature's most feared winds. Some clouds seed their own destruction by turning droplets into ice. A cloud can carry within it the process that will help make it disappear. In certain cold cloud layers, supercooled liquid droplets remain suspended until ice crystals begin to form. Once they do, the balance changes quickly, because water vapor is more eager to deposit onto ice than remain with liquid droplets under those conditions. The crystals grow larger while nearby droplets evaporate, feeding the ice even more. Eventually, the crystals or snowflakes become heavy enough to fall out. As moisture is stripped away, the cloud can thin, break, or vanish entirely. What began as a suspended field of liquid droplets has created the seeds of its own decline. This is one reason clouds are such dynamic systems rather than static objects. Their internal microphysics can change their fate from within. A quiet cloud may already be beginning to undo itself, preparing precipitation and losing the droplets that first made it visible. Destruction, in this case, arrives as a phase change. One storm cloud can hold several different kinds of precipitation at once. Inside a mature thunderstorm, different layers and regions can produce very different outcomes at the same time. Near the upper parts, snow and ice crystals may be forming in bitter cold air. Elsewhere, hailstones may be circulating through powerful updrafts. Lower down, raindrops may be growing or melting from frozen particles that fell from above. In another part of the same cloud, supercooled droplets may still be waiting to freeze. All of those processes can exist together within one towering structure because the storm contains strong vertical motion, sharp temperature contrasts, and separate internal zones of growth and descent. That is why the weather reaching the ground can vary so suddenly over short distances. One neighborhood may get heavy rain, another hail, and another gusty outflow with little precipitation at all. A thunderstorm is not one simple reservoir. It is a layered factory, producing several versions of falling water at once before gravity sorts out what arrives below. Mountains can force air upward and create clouds in minutes. A mountain does not need to touch the sky to shape it. When moving air meets a ridge, slope, or summit, it cannot pass straight through the rock, so it is pushed upward. As that air rises, it cools. If it cools enough, moisture condenses almost at once, and a cloud can appear where there was clear blue only moments earlier. This is why peaks so often gather scarves, caps, and banners of cloud, while the valleys stay open below. The mountain acts like a machine that lifts the atmosphere into visibility. In windy conditions, the process can be astonishingly fast. Air flows, cools, condenses, and a cloud seems to switch on over the summit. Then, if the air changes or dries, it can vanish just as quickly. These clouds reveal something profound. Land is not separate from weather. A mountain can reach up into the moving air and pull a cloud out of it. Forests help feed the sky with moisture that becomes cloud. A forest does far more than stand beneath the weather. It actively helps create it. Trees draw water from the soil and release part of it back into the air through tiny openings in their leaves. This process, called transpiration, sends huge amounts of moisture upward every day. In dense forests, the combined effect is extraordinary. Millions of leaves become a living pump, lifting water from the ground and adding it to the atmosphere above. That extra moisture can help raise humidity, support cloud formation, and influence when rain returns. In some places, the forest and the sky become partners in a cycle that sustains both. Water falls, roots draw it in, leaves release it, and clouds build again overhead. A woodland is not just a collection of trunks and branches. It is part of a hidden vertical river, moving water from the earth into the air and helping stitch the living landscape to the clouds above. Oceans supply most of the water vapor that clouds are made from. When you look up at a cloud drifting over land, there is a good chance part of its story began far out at sea. The oceans cover most of our planet, and under the warmth of sunlight, they continuously release water vapor into the atmosphere. Every wave, swell, and broad expanse of sunlit surface helps feed that invisible supply. Winds then carry the moisture away, sometimes across enormous distances, where it may later condense into cloud, fog, rain, or snow. In this sense, the sea is the great reservoir behind much of the sky. Even inland weather often depends on moisture that once rose from distant ocean water. That connection makes clouds part of a planetary cycle rather than a local event. A cloud above a mountain town, a farm, or a city may owe its existence to evaporation that happened hundreds or thousands of miles away. The sky is often carrying water that has crossed an ocean before it became visible. Tropical rainforests help build cloud systems that shape distant weather. A rainforest is not only a place where clouds arrive. It is a place that helps send them outward. In tropical forests, intense heat, deep vegetation, and vast supplies of moisture combine to fuel powerful daily exchanges between land and sky. Water evaporates from wet surfaces. Leaves release more through transpiration. Warm air rises. Clouds build. Then, through circulation and wind, that moisture can be carried far beyond the forest itself. Some scientists describe these pathways as atmospheric rivers in the sky, streams of vapor that help influence rainfall in distant regions. In South America, for example, moisture linked to the Amazon contributes to weather patterns far from the forest basin. This means a cloud forming over a distant field or city may be connected to moisture first lifted by trees deep in the tropics. A rainforest can help right weather far away. It does not simply live under the atmosphere. It helps power part of the atmosphere's own reach. Sea breeze fronts can spark afternoon cloud towers near coasts. Coastlines often become weather factories by afternoon, even on days that begin calm and bright. Land heats faster than water under the sun. So by midday, the air over land grows warmer and rises more readily. Cooler marine air then pushes inland to replace it, creating the sea breeze. Where that incoming air meets hotter air already sitting over the shore or just inland, the boundary can act like a miniature front. Air is forced upward along it. If enough moisture is present, cumulus clouds begin to build, sometimes quickly and dramatically. Along some coasts, these lines of rising air can produce cloud streets, showers, or full afternoon thunderstorms, while the sea offshore remains relatively clear. This gives coastal weather a daily rhythm that feels almost choreographed. Morning can be open and blue. Then the breeze arrives, the boundary sharpens, and the sky starts constructing towers. A strip of shoreline becomes the meeting place of sea, land, heat, and cloud. Cities can influence clouds by adding heat and tiny airborne particles. A city changes the atmosphere even before a cloud appears. Concrete, asphalt, brick, and rooftops absorb and hold heat, often making urban areas warmer than surrounding countryside, especially after sunset. This extra warmth can encourage rising air and alter local circulation. At the same time, traffic, industry, construction, and human activity add countless particles to the air. These tiny bits of matter can act as surfaces on which moisture condenses. Together, extra heat and extra particles can affect where clouds form, how dense they become, and sometimes how likely they are to produce precipitation. The influence is not always simple, and it varies with season, geography, and wind, but the effect is real enough that cities can shape their own slice of sky. A skyline does not merely sit beneath weather patterns arriving from elsewhere. It can modify the atmosphere around it. Human-built landscapes can change the conditions in which clouds are born and grow. Wildfire smoke can create strange clouds and even their own storms. A large fire does not only burn across the ground. It can begin building weather overhead. Intense heat from a wildfire drives air upward in powerful columns, carrying smoke, ash, moisture, and hot gases high into the atmosphere. As the rising plume cools, water vapor can condense around the particles, forming towering clouds above the fire itself. These are called pyrocumulus when they remain smaller, and pyrocumulonimbus when they grow into full storm clouds. At that stage, the fire has helped create something astonishing, a thunderstorm born from flame. Such clouds can produce lightning, strong winds, and turbulent downdrafts, which may worsen the fire below or even start new ones. The smoke can also be injected far upward and carried across continents. So a wildfire can transform from a ground event into an atmospheric engine. The forest burns, the air surges upward, and above the flames the sky begins making clouds from heat, ash, and destruction. Volcanic ash can seed clouds with particles from deep inside Earth. When a volcano erupts, it does more than throw rock and ash into the air. It also sends countless microscopic particles into the atmosphere, and those particles can become sites where moisture gathers. In that sense, material from deep within the planet can help shape what happens far above it. Volcanic ash and gases can influence cloud formation around the eruption itself, and larger eruptions can affect the atmosphere on much broader scales. Water may condense on the particles, creating billowing clouds that mingle steam, ash, and weather in one extraordinary scene. The visual effect can be surreal, a sky in which geology and meteorology suddenly overlap. There is also something profound about the source. A cloud may begin with fragments of magma ground fine and launched upward from the Earth's interior. The ground below erupts, and the sky above responds. A volcano can seed the atmosphere with particles that once lay hidden beneath mountains, crust, and molten stone. Dust from the Sahara helps build clouds over the Atlantic. One of the world's great cloud stories begins in a desert. Powerful winds over the Sahara can lift enormous quantities of dust high into the atmosphere and carry them westward across the Atlantic Ocean. These plumes travel astonishing distances, sometimes reaching the Caribbean and the Americas. Along the way, the dust particles influence the atmosphere in several ways. They can provide surfaces for condensation or ice formation, affect how sunlight is absorbed and scattered, and alter the stability of air masses through which they move. That means a storm or cloud deck far from Africa may still bear the fingerprint of Saharan dust. The idea is almost cinematic. Sand from ancient dry landscapes rises, crosses an ocean, and helps shape the sky over another continent. Earth's systems are deeply connected, and clouds make those connections visible. A tropical cloud field over blue Atlantic water may partly owe its existence to grains lifted from one of the driest places on the planet. Even bacteria can help droplets freeze inside some clouds. It is astonishing enough that dust and salt help shape clouds, but some living things play a role as well. Certain bacteria carry surface structures that are especially effective at helping ice begin to form. When those bacteria or fragments of them are lifted into the atmosphere, they can act as biological ice nuclei. In cold clouds, that matters enormously. A droplet that might have remained liquid can freeze once it encounters the right microscopic trigger. This means the boundary between biology and weather is more intimate than it first appears. Material from plants, soils, or living systems below can rise into the air and affect the microphysics inside a cloud. Scientists are still working out how important these biological particles are in different environments, but the fact itself is extraordinary. Something as small as a bacterium can help decide whether moisture stays liquid or becomes ice. Life on the ground can influence the behavior of water far above it. Cloud droplets are too small to fall until they combine. A cloud can hold an enormous amount of water without producing any rain, because most of its droplets are tiny beyond ordinary imagination. Each one is so small and light, but air resistance easily counters its fall. Instead of dropping, the droplets remain suspended, drifting within the cloud as currents carry them. For rain to begin, those tiny droplets usually need to collide and merge into larger drops. Once they grow enough, gravity starts to win. Then the cloud changes from a floating collection of microscopic beads into a source of falling water. This helps explain why many clouds never rain at all. They contain moisture, but not yet in the right form. The process of making raindrops is therefore a story of accumulation and chance. Billions of small particles must find ways to become fewer, larger ones. A rain shower begins when the cloud's water stops being almost weightless and starts becoming heavy enough to descend. Clouds disappear when air warms or dries enough to erase them. A cloud can feel substantial while it lasts, yet it survives only within a narrow balance of temperature and moisture. If the surrounding air becomes warmer, the droplets or crystals may evaporate back into invisible vapor. If drier air mixes in, the same thing can happen even without much warming. That is why cloud edges often fray, thin, and vanish in sunlight or shifting wind. The cloud is not moving somewhere else intact. Part of it is literally ceasing to exist as a visible object. This makes the atmosphere feel almost like a stage where forms appear and are withdrawn according to conditions we cannot see directly. A brilliant cloud bank may look permanent, then fade in minutes once the balance changes. That fragility is part of their fascination. They are made from water, but their visibility is delicate. The sky does not need to tear a cloud apart physically. It only needs to warm or dry the air enough, and the cloud is gone. The flat base of a cumulus marks where condensation begins. That crisp horizontal underside is one of the most revealing shapes in the sky. A cumulus cloud often looks rounded and irregular above, yet its base can appear surprisingly even, as though someone drew a straight line across the atmosphere. The reason is that rising air reaches a particular height where it cools enough for water vapor to condense into visible droplets. Below that level, the air parcel is still too warm for cloud to form. Above it, condensation begins. Because many rising parcels in the same area reach that threshold at roughly the same height, the cloud base lines up into a flat bottom. In one simple shape, a cloud is showing you the altitude where invisible moisture turns visible. That makes a cumulus base more than a visual detail. It is a measurement written across the sky. The atmosphere has marked the lifting condensation level for anyone patient enough to notice the remarkable straightness beneath the billowing white top. Rising air builds clouds, and sinking air tears them apart. A cloud is often the visible result of upward motion. Air rises, expands, cools, and allows moisture to condense. That is the constructive side of the atmosphere, the part that builds towers, layers, and veils from invisible vapor. But the reverse is just as important. When air sinks, it is compressed, and compression warms it. Warmer air can hold more water as vapor, so the droplets or crystals that made the cloud begin to evaporate. In this way, downward motion can dissolve clouds from within. The sky is therefore shaped by an ongoing contest between lifting and sinking, between visible formation and invisible erasure. A bright cumulus afternoon may collapse when sinking air spreads across the region. A storm may sharpen at one edge where air rises and clear at another where it sinks. Clouds are not just passive moisture. They are markers of motion. To watch them grow or fade is to watch vertical air currents revealing themselves. Stable air spreads clouds wide, while unstable air builds them tall. The atmosphere has moods, and clouds reveal them. In stable conditions, rising air resists continued ascent. It may lift a little, cool, and condense, but then it tends to spread sideways rather than keep climbing. The result is often broad sheets, layered decks, or smooth cloud forms that stretch far more than they rise. In unstable conditions, the story changes. Once air starts rising, it remains warmer than its surroundings and keeps going. That encourages vertical growth, producing towers, build-ups, and the great upward architecture of storms. So the shape of a cloud is often telling you whether the atmosphere is suppressing ascent or encouraging it. A layered sky speaks of restraint. A sky full of growing columns speaks of acceleration. This makes clouds a kind of emotional display for the air itself. They show whether the atmosphere is settling things down or letting them run upward. Width and height are not just appearances. They are clues to the balance of the day. The same sky can hold clouds moving in different directions. To someone standing on the ground, the sky can seem like one broad dome with one shared motion. Yet different layers of the atmosphere often flow independently, each with its own wind speed and direction. That means low clouds may drift one way while higher wisps streak another, and still higher ice clouds may move faster in yet a third direction. If you watch carefully, the sky begins to feel less like a single ceiling and more like stacked rivers sliding past one another. This layered motion is one reason cloud watching can be so revealing. It shows structure in the atmosphere that you would never sense from the surface alone. A calm breeze at ground level tells you almost nothing about what is happening miles above. Clouds reveal those hidden currents. Different directions, different speeds, different histories of moisture can all coexist at once. The result is a sky with depth, a moving architecture built from separate levels of air flowing through each other. Wind shear can twist a growing storm into a rotating supercell. A thunderstorm becomes especially dangerous when the winds around it change with height in the right way. If wind speed increases upward, or the direction shifts from one layer to another, the atmosphere begins with horizontal spin already built into it. Then a strong storm updraft can tilt that horizontal rotation upright. Once vertical, the rotation can become organized inside the storm and help create a supercell, one of the most powerful and persistent thunderstorm types on Earth. This rotating structure can support giant hail, intense lightning, destructive winds, and sometimes tornadoes. What makes the process so fascinating is that the twist begins before the storm fully forms. The ingredients are layered into the wind itself. The cloud is not inventing rotation from nothing. It is grabbing hold of motion already present in the atmosphere and turning it into a rotating engine. A supercell is what happens when a storm finds the right kind of wind and learns how to spin. Moisture, lift, and cooling are the essential ingredients of cloud birth. However strange a cloud may look once it forms, its beginning is built on a simple trio. First, there must be moisture in the air, invisible water vapor waiting for the right moment. Second, the air usually needs to be lifted. That lift can come from sunshine warming the ground, from a mountain slope, from a front, or from converging winds. Third, the lifted air must cool enough for condensation to begin. When those ingredients come together, the unseen becomes visible. Droplets or crystals appear, and a cloud enters the world. Remove one ingredient, and the process often fails. Dry air cannot make much cloud. Air that never rises may keep its moisture hidden. Air that rises but does not cool enough remains clear. This is part of what makes clouds so satisfying to understand. Even the most elaborate sky display begins with a small set of physical rules. The atmosphere is infinitely varied, yet every cloud starts with this basic recipe. Clouds often reveal invisible atmospheric layers stacked above one another. Sometimes the sky looks simple from below, but a closer look shows several different cloud types occupying different heights at the same time. Low puffs may drift beneath a middle sheet, while thin, icy streaks cross far above both. Each layer forms where temperature, humidity, and wind happen to suit a particular kind of condensation. That means the sky can act like a cross-section of the atmosphere, revealing stacked zones that would otherwise remain entirely unseen. A meteorologist reads those layers almost like pages. One tells of moisture near the surface. Another hints at a front or wave aloft. A third may signal cold air and strong winds high overhead. Even to an ordinary observer, the effect is fascinating because it gives the sky depth. It is no longer one surface. It is a structured volume with distinct levels, each running on different rules. When several layers appear together, the atmosphere is briefly exposing its internal architecture in visible form. Sunlight can evaporate the edges of a cloud before your eyes. A cloud is not only shaped by wind and moisture. Light itself can help redraw it. Along the edges of many clouds, sunlight warms the surrounding air or the droplets directly enough to encourage evaporation, especially where the cloud is already thin. That is why bright margins often fray, shrink, and peel away in slow motion. You can sometimes watch a once solid puff lose a corner, then a whole side, as sunlight and drier mixing air nibble at it. The effect is subtle but mesmerizing, because it lets you see a cloud being erased in real time. The sky becomes a place of active editing. Illumination is not just something that makes a cloud visible or beautiful. It can help determine how long the cloud survives. This gives sunlight a double role in the sky. It paints clouds with brightness, and it also helps dissolve them. A glowing edge may already be the place where disappearance has begun. Polar stratospheric clouds can glow with eerie colors in winter. These are not ordinary clouds drifting through the lower sky. They form far higher, in the stratosphere, where the air is extremely dry and bitterly cold. That is why they are so rare. Temperatures must plunge low enough for tiny particles of ice or nitric acid compounds to gather, often in the dark polar winter. When sunlight finally reaches them at the right angle, they shine with astonishing colors: pearl, violet, green, and rose, as if the sky has turned to polished glass. People who see them often describe them as unnatural, because the glow feels too bright and too smooth to belong to weather. Yet what makes them truly fascinating is their setting. These clouds appear in a part of the atmosphere where most clouds never exist. They are winter's highest ornaments, suspended above the usual world of wind and rain, revealing that even the most remote layers of air can suddenly become visible and spectacular. These rare clouds help create the chemistry behind the ozone hole. Their beauty hides a dangerous role. In the frigid polar stratosphere, these clouds provide surfaces on which unusual chemical reactions can take place. Substances containing chlorine and bromine, many of them released by human-made compounds, can be transformed there into far more reactive forms. During the dark polar winter, those reactive ingredients build up quietly. Then, spring sunlight returns, and the reactions accelerate. Ozone molecules begin to break apart much faster than usual, especially over Antarctica, where the cold is intense and persistent. That is why the ozone hole is not simply a story about gases floating in the sky. It is also a story about cloud particles acting as chemical workbenches in one of the coldest parts of the atmosphere. So, these clouds matter far beyond their appearance. They help turn silent winter air into the stage for one of the most important environmental lessons ever learned about human influence on the upper sky. Noctilucent clouds shine at the edge of space after sunset. They appear when the rest of the sky has already gone dark, which is why they feel almost impossible. These clouds form at extraordinary heights, far above ordinary weather, in the mesosphere near the boundary where space begins to feel close. There, the air is so thin and cold that tiny ice crystals can gather on microscopic particles. Because of their altitude, they can still catch sunlight long after sunset for people on the ground. The result is a ghostly blue-white glow, delicate and electric, hovering against a darkening sky. They often appear in fine ripples, streaks and curls, which makes them look more like brushed silver than cloud. For most of human history, no one seems to have recorded them before the late 19th century, which adds to their mystery. When you see them, you are looking at one of the highest visible phenomena in Earth's atmosphere, a shining lacework suspended where air is fading towards space. Noctilucent clouds may be growing more common as the upper atmosphere changes. That possibility is one reason scientists watch them so closely. These clouds are sensitive to conditions in the high atmosphere, especially temperature and the amount of water vapor present in that rarefied region. Research suggests they may be appearing more often or more brightly in some places than in the past. One possible reason is that changes driven by greenhouse gases can cool the upper atmosphere even while warming the lower one. Another is that methane can eventually contribute to extra water vapor at those heights. If so, these glowing clouds may be acting like distant messengers, revealing changes in parts of the atmosphere that few people ever think about. That gives them a strange double identity. They are beautiful objects for summer twilight watching, yet they may also be clues in a much larger climate story. A shimmering cloud near the edge of space could be telling us that the upper sky itself is quietly being altered. Pyrocumulus clouds rise above wildfires like storms born from flame. There is something deeply unsettling about a fire that begins to make its own cloud. When flames become intense enough, they heat the air above them so strongly that it rises in a powerful column. That rising air carries smoke, ash, water vapor, and burning debris upward. As it cools, moisture condenses, and a cloud forms directly over the fire. The result can look like a thunderhead rooted in flame, a column climbing from burning forest into the sky. These clouds reveal just how much heat a large wildfire is releasing. The fire is no longer only consuming land. It is pushing hard enough on the atmosphere to build visible weather overhead. People nearby may see the plume boiling upward, changing color, widening, and taking on the shape of a growing storm. It is one of nature's starkest reminders that fire and sky are not separate systems. Under extreme conditions, a wildfire can reach upward and start constructing its own cloud world above the flames. Pyrocumulonimbus clouds can loft smoke all the way into the stratosphere. Once a fire-driven cloud grows large enough, it can cross into a new level of atmospheric importance. A pyrocumulonimbus is not merely a smoky tower. It is a full storm generated by extreme fire behavior, with strong vertical motion, capable of punching smoke and ash far higher than most ordinary plumes could ever reach. In the most powerful cases, material is injected into the stratosphere, where it can remain for long periods and travel great distances around the globe. That gives a wildfire consequences far beyond the burning landscape itself. Smoke from one region can influence skies, sunsets, and atmospheric conditions thousands of miles away. Some of these storm clouds can also generate lightning, which may ignite new fires and create a dangerous chain reaction. So the process becomes self-expanding. Fire creates a storm. The storm spreads smoke high above ordinary weather. The smoke persists and travels. A burning forest can briefly behave like a volcanic eruption written in smoke and cloud. Some storms produce green skies when light passes through ice and rain. The sight can be deeply unnerving. A sky that should be grey, white or blue takes on a strange green cast, often before or during severe weather. This is not because the storm contains some exotic substance. It is an optical effect, and it tends to happen when sunlight is low in the sky and passes through a deep storm packed with water and ice. The red and yellow tones of late-day sunlight, combined with the blue scattering already present in the atmosphere, can interact with the storm's dense interior in a way that creates that eerie green appearance. Large hail and heavy rain are often associated with such storms, though the green color itself does not cause them. What makes the effect so memorable is emotional as much as physical. The familiar rules of daylight seem to fail. The world looks briefly alien. Then thunder rolls and the storm arrives. A severe storm can change not only the weather, but the very color of the sky. Cloud iridescence happens when sunlight bends through nearly identical droplets. It is one of the most delicate color displays in the atmosphere. Near the edge of a cloud, especially a thin cloud made of very small droplets of nearly uniform size, sunlight can be diffracted and spread into soft pastel bands. The colors may shimmer in pink, green, blue, or gold, often so faint that people mistake them for tricks of the eye. Unlike the stronger geometry of a rainbow, iridescence often appears in patches, fringes, or luminous stains near the sun. What makes it possible is remarkable precision. The droplets or tiny particles in that part of the cloud must be similar enough in size for the light waves to interfere in an organized way. So a cloud that looks casual and irregular from the ground may briefly become a finely tuned optical instrument. The result is exquisite because it feels almost accidental. A thin edge, the right droplets, the right angle, and suddenly the cloud is wearing colors like oil on water. A glory forms when sunlight rings your shadow with cloud-made color. Imagine standing above mist or cloud with the sun behind you and seeing your own shadow cast forward onto the vapor below. Around the shadow's head appears a set of luminous colored rings, sometimes faint, sometimes vivid. This is the glory, one of the strangest and most intimate optical effects in the sky. It happens when sunlight interacts with tiny droplets in the cloud or mist and is scattered back toward the observer in a special way. Unlike a rainbow which appears in a different part of the sky, the glory is centered on your own line of sight. That means each observer sees a glory around their own shadow, not someone else's. The effect can make a person feel unexpectedly central to the atmosphere, as though the cloud has made a halo just for them. Yet the explanation is pure physics. Water droplets and sunlight combine to frame your shadow in color, turning mist into a private ring of light. Brocken specters can turn a person into a giant on mist. On a mountain ridge or high slope, if the sun is behind you and cloud or fog lies below, your shadow can be thrown outward onto that vapor and appear enormous. The figure may seem to tower across the mist with impossible scale, surrounded at times by a glory of colored rings. This is the Brocken specter, named after a mountain in Germany long associated with such sightings. What makes it so eerie is perspective. The shadow falls on a surface whose distance is hard to judge, and the mist shifts constantly, so the figure can seem to move, swell, and loom with supernatural size. For earlier observers, it was easy to imagine spirits, apparitions, or warnings in such a vision. Even knowing the science does not entirely remove the thrill. Your own body, translated into light and vapor, becomes a colossal presence suspended in cloud. The mountain lends you a giant double, and for a moment the sky appears to answer back with your own impossible form. Pilots read clouds like maps of danger, lift, and hidden turbulence. To someone in an aircraft, clouds are not merely scenery. They are information. A smooth, layered cloud may suggest one set of flying conditions, while towering build-ups hint at powerful vertical motion. Lenticular forms can warn of mounting waves and severe turbulence. Ragged scud under a storm, sharp anvil edges, overshooting tops, and lines of towering cumulus all speak a language of airflow, moisture, and risk. Pilots learn to interpret that language because the sky can hide hazards invisible from the cockpit until it is too late. Icing may lurk in one cloud type. Violent updrafts may be building in another. Yet clouds can also reveal opportunity. Glider pilots use visible signs of lift to stay aloft, reading cumulus development and cloud streets like clues on a map. This gives cloud watching in flight a special intensity. The shapes outside the window are not passive beauty. They are the visible signatures of forces that can help, hinder, or endanger the journey through the air. Sailors once used cloud shapes to guess tomorrow's weather at sea. Long before satellites, radar, or modern forecasting, people who lived by the ocean learned to study the sky with serious attention. Sailors watched for high wisps arriving ahead of a front, for thickening layers that meant a change was moving in, for the clearing patterns that followed a blow, and for dark, growing towers that warned of squalls. At sea, those signs mattered enormously, because weather could decide safety, speed, or survival. A captain who understood clouds understood something about wind shifts, rain, and pressure changes long before instruments made those patterns easier to track. This knowledge was practical, repeated, and sharpened by experience. It turned the sky into a set of hints about what lay just beyond the horizon. What makes that tradition fascinating is that it joined observation and instinct. Sailors did not know every mechanism in modern scientific terms, yet many of their readings were remarkably sound. The open ocean taught people to treat clouds not as background, but as messages. Farmers have watched clouds for centuries to time planting and harvest. For a farmer, clouds were never just beautiful. They were clues about risk, moisture, and the narrow windows in which work had to be done. A run of high, thin cloud might suggest a change coming. A sky building thicker layers could mean rain was near. Towering afternoon growth in summer might warn that cut hay needed gathering quickly before a storm arrived. Generations learned to pair local knowledge of land and season with close observation of the sky. That did not make cloud reading perfect, but it made it practical. When to plant, when to plow, when to bring in grain, when to protect animals, All of these choices could depend partly on what was happening overhead. In that sense, clouds were woven into agriculture long before scientific meteorology offered formal models. They were part of the rhythm of work. The field and the sky were in constant conversation, and people who lived from the land had to learn how to listen. Ancient people often saw gods, spirits, or omens in cloud forms. That response makes a kind of sense. Clouds are changeable, towering, luminous, and often beyond human control. They can bring life-giving rain, violent storms, strange colors, or shapes that seem briefly deliberate. It is no surprise that many cultures treated them as signs of divine presence or intention. In some traditions, storm clouds were linked with sky gods, thunder beings, or celestial battles. In others, unusual cloud forms were read as omens of change, warning, or favor. People saw armies, faces, animals, or entire narratives in the shifting sky because the atmosphere so easily invites interpretation. A massive thunderhead can feel purposeful. A strange halo or glowing cloud can feel like a message. These meanings differed from place to place, yet the underlying impulse was shared. The sky seemed alive with power and symbolism. Before cloud physics existed, clouds still demanded explanation, and myth was one of humanity's earliest ways of answering the drama overhead. Artists painted clouds long before science explained how they worked. Painters noticed subtleties in the sky long before meteorology became a formal science. They studied how clouds change with light, how storms build weight on a horizon, how high wisps differ from low swollen masses, and how weather can alter the emotional tone of an entire landscape. In many periods of art, clouds were not decorative extras. They were central to mood, scale, and drama. A calm, layered sky could make a scene feel serene. A dark, advancing storm could make the same scene feel charged with destiny. Some artists became such close observers, but modern viewers can often identify real cloud types in their work. That is part of what makes old paintings fascinating to look at now. They preserve not only imagination, but observation. Before people fully understood the physics of condensation, instability, and atmospheric layers, artists were already recording the visual truth of the sky with remarkable sensitivity. They painted clouds as living structures, because that is exactly what they saw. Luke Howard gave clouds the names we still use today. In the early 19th century, an English observer named Luke Howard did something deceptively simple and enormously influential. He created a naming system for clouds based on their appearance and behavior, using Latin terms such as cirrus, cumulus, and stratus. Before that, people described clouds in many loose or poetic ways, but Howard's system gave the sky a clear shared vocabulary. That mattered, because once clouds had stable names, observers in different places could compare what they saw with far greater precision. Scientists, artists, and ordinary weather watchers alike could speak the same language. Howard's choices were elegant because they captured the essential forms without making the system cumbersome. A wispy, high cloud, a piled heap, a spread-out layer, these became categories that still structure cloud classification today. It was a quiet revolution in naming. He did not change the sky itself, yet he changed how people could talk about it, remember it, and begin studying it systematically. Early meteorologists learned that clouds could classify the moving atmosphere. Once cloud names existed, they became more than labels. They became tools. Early meteorologists realized that different cloud forms were associated with different processes in the atmosphere: rising air, layered cooling, approaching fronts, storm growth, and changing stability. A cloud type was therefore not only a visible object, but evidence about what the air was doing. That insight helped transform weather study from scattered description into a more organized science. Instead of treating every cloud as an isolated curiosity, observers could begin linking forms to patterns and patterns to forecasts. A sky of advancing cirrus and thickening layers meant something different from a sky full of bubbling cumulus or one covered by low stratus. The atmosphere was no longer just a source of unpredictable appearances. It was a system with readable structure. Clouds became one of the first ways people could classify motion in the air itself. The sky offered categories, and those categories helped unlock weather's deeper order. Satellite images turned clouds into global patterns instead of local mysteries. Before satellites, people mostly knew clouds from the ground, or at best from scattered aircraft reports. That meant even experienced observers were seeing only pieces of much larger systems. Satellites changed everything. Suddenly, clouds could be viewed from above, across entire oceans, continents, and polar regions at once. A hurricane was no longer just wind and rain at one coastline. It became a spiral visible in full. A frontal system could be traced across nations. Vast decks of marine cloud, thunderstorm clusters, jet stream streaks, and polar swirls all emerged as parts of global circulation rather than isolated weather events. This shift was profound because it gave humanity a planetary perspective on the atmosphere. Clouds stopped being only local experiences and became visible expressions of Earth-scale motion. We could finally watch the whole machine working. The sky, seen from space, revealed itself not as a scattered collection of passing shapes, but as a connected moving system that wraps the entire planet. Weather radar reveals storm clouds as hidden structures, not flat shapes. From the ground, a storm can look like a dark wall or tower, impressive but mysterious. Radar changed that by allowing meteorologists to probe inside precipitation and map where rain, hail, and rotating structures are developing. Instead of seeing only the outside of a storm, scientists can detect hook echoes, squall lines, cores of intense rainfall, bowing wind structures, and other internal features that reveal what the cloud is really doing. Modern radar can even estimate motion within the storm, showing where air is moving toward or away from the radar site. That means a thunderstorm becomes less like a silhouette and more like a living three-dimensional machine whose internal organization can be tracked in real time. This has transformed warning systems, especially for severe storms and tornadoes. What once appeared as a single threatening shape in the distance is now understood as a structured process with identifiable parts. Radar lets us look through the curtain and see the architecture within. Modern forecasts still depend on watching how clouds form and evolve. For all the power of satellites, radar, aircraft data, and computer models, clouds remain one of the atmosphere's most important visible clues. Forecasters watch where they appear, how quickly they grow, whether they flatten or tower, how they spread, and how they interact with fronts, terrain, and heat from the ground. A model may predict storms, but the real sky shows whether the atmosphere is actually following that script. The first bubbling cumulus of the day, the stubborn marine layer that refuses to clear, the sudden eruption of convective towers, all of these can confirm or challenge what the forecast expected. In that sense, cloud watching is not an outdated art left behind by technology. It is still part of the working science of prediction. Clouds show the atmosphere becoming real in front of us. Even now, some of the most advanced weather understanding begins with the ancient act of looking up and noticing what the sky is starting to do. Clouds help cool Earth by reflecting a portion of sunlight. From space, some of the brightest parts of our planet are not ice caps or deserts, but cloud tops. They act like shifting mirrors, sending part of the sun's energy back into space before it can warm the surface below. that reflective power matters enormously. A world with no clouds would absorb more sunlight overall, and the balance of Earth's climate would be very different. The effect is easy to feel in everyday life. Step from open sunshine into the shadow of a thick cloud, and the temperature can drop at once. Now imagine that effect scaled up across oceans, continents, and entire seasons. Vast decks of cloud can dim the planet on a global level. What makes this so fascinating is that something soft and fleeting can help regulate the temperature of an entire world. A cloud may last only hours, yet while it exists, it is part of Earth's shield, turning sunlight away before it ever reaches the ground. Clouds also trap heat, which makes them one of climate's great puzzles. A blanket and a mirror in the same sky. That is what makes clouds so difficult to understand. During the day, many clouds reflect sunlight and help keep the surface cooler. But they also absorb and re-emit heat rising from the earth below, especially after dark. That means the same cloud cover that softens daytime warmth can slow nighttime cooling. Anyone who has felt a cloudy evening stay milder than a clear one has experienced this directly. On the scale of climate, that double role becomes extraordinarily important. Some clouds cool more than they warm. Others do the reverse. Their height, thickness, droplet size, and location all matter. So clouds are not just part of the climate system. They are one of its most complicated controls. They can oppose warming and reinforce it at different times. The atmosphere's most familiar shapes are also among its most difficult to predict, because every cloud is balancing sunlight and heat at once. Low clouds usually cool the planet more than high clouds do. A cloud's altitude changes its influence on climate. Low clouds, especially broad, bright ones over oceans, are very effective at reflecting sunlight back into space. Because they sit near the surface, they are not especially powerful at trapping heat compared with higher clouds. That gives them a net cooling effect in many situations. High clouds behave differently. They are colder and often thinner, which makes them less reflective than the brightest low decks, yet better at absorbing and re-emitting heat from below. So when scientists compare the two, low clouds often come out as stronger planetary coolers. This is why a dull, white marine cloud layer can matter far more to global temperature than it seems from the ground. It may not look dramatic, but it is doing large-scale radiative work every hour it persists. The sky is arranged vertically, and that vertical arrangement matters. A cloud's height can help decide whether it acts more like shade or insulation. High, thin clouds can warm Earth by holding heat below. They often look delicate, almost harmless, stretched in pale streaks across the upper sky. Yet those high ice clouds can play a powerful climatic role. Because they are cold and relatively translucent to incoming sunlight, they do not reflect as much solar energy as thicker, lower clouds. At the same time, they are very effective at interacting with infrared heat rising from the warmer surface below. They absorb some of that outgoing energy and re-emit it, including back downward. The result is a warming influence, especially over longer timescales. This is one reason thin cirrus layers matter so much in climate studies. Their beauty can hide their effect. A veil of icy cloud high above may be helping keep a little more warmth in the Earth's system than would otherwise escape to space. They are like transparent curtains in the upper atmosphere, not shutting out the sun completely, but slowing the planet's loss of heat. Small changes in clouds can shift temperatures across the whole planet. Climate is so finely balanced that even modest alterations in cloud cover, height, brightness, or persistence can have global consequences. If low reflective clouds become slightly less common in key regions, more sunlight reaches the surface. If warming leads to more high, thin clouds in certain zones, more heat may be retained. These changes do not need to be dramatic in appearance to matter. A fractional shift spread across oceans and continents can influence Earth's temperature over years and decades. That is what makes clouds so powerful and so unsettling from a scientific point of view. They're not fixed features. They respond to temperature, moisture, circulation, and particles in the air. Then in turn, they affect those same conditions. It is a feedback system written in vapor and light. A slight change in how often particular clouds appear, or where they linger, can ripple outward until it alters the energy balance of the entire planet. Scientists still debate exactly how clouds will amplify climate change. This is one of the biggest open questions in climate science. Researchers agree that greenhouse gases are warming the planet, but clouds make it harder to pin down exactly how strong that warming will become. The reason is that clouds respond to climate shifts in complex ways. Warming may change where clouds form, how bright they are, how long they last, and how high they reach. Some of those changes could reduce cloud cooling and amplify warming. Others could offset part of it. Different regions may behave differently, and the smallest cloud processes are difficult to represent perfectly in large global models. So even with satellites, aircraft measurements, and supercomputers, scientists are still working to narrow the uncertainty. That is not a sign of confusion about the basics of climate change. It is a sign of how subtle and influential clouds really are. The sky's most familiar features may help determine just how hot Earth's future becomes. Without clouds, Earth's days would be hotter and nights colder. Clouds smooth out the planet's temperature extremes. In daytime, they can reduce incoming sunlight and keep the surface from heating as strongly. At night, they can hold back some of the heat that the Earth is trying to radiate away into space. Remove them, and the contrast sharpens. Days become brighter, harsher, and hotter. Nights cool more rapidly and fall farther. This pattern is easy to notice on a small scale. Clear desert climates often swing between scorching afternoons and cold nights. Cloudier regions tend to have more moderated daily temperatures. Now imagine that principle applied globally. A cloudless Earth would still have an atmosphere, but it would lose one of its great balancing tools. The familiar softening effect of overcast skies and cloud-filled nights would be gone. The planet would become more extreme in its daily rhythm. Clouds are not merely weather. They are part of the mechanism that keeps Earth from lurching too far between heat and chill every single day. Cloud cover can protect glaciers from sunlight or speed their melting. It depends on the kind of cloud, the season, and the timing, which is exactly what makes the relationship so fascinating. Thick clouds can shield snow and ice from direct solar heating, helping preserve bright surfaces that would otherwise absorb more energy under clear skies. In that sense, cloudy conditions can act like temporary protection for glaciers. But clouds can also warm the air, increase downward long-wave radiation, and sometimes enhance melting, especially in places where sunlight is already weak, or during seasons when heat trapping matters more than shading. So a glacier under cloud is not simply safer or more threatened. It is caught in a more complicated exchange. The sky above ice can either slow melt or encourage it depending on context. This matters greatly for places like Greenland and mountain glacier systems, where even subtle changes in cloud behavior can influence ice loss. A passing cloud can therefore become part of a much larger story about frozen landscapes and their future. Marine stratocumulus clouds help regulate temperatures over vast ocean regions. These clouds may not look dramatic from the ground, but from above, they form some of the largest and most climatically important cloud fields on Earth. They often spread across cool eastern ocean basins in enormous low decks, bright and extensive enough to reflect vast amounts of sunlight. Because they cover such large areas for long periods, their cooling effect is profound. They help keep underlying seas cooler, influence air circulation above them, and shape coastal climates on nearby land. Some of the world's major fisheries and coastal weather regimes exist partly under their influence. What makes them especially important is their persistence. A thunderstorm can be spectacular, but brief. Marine stratocumulus can endure and dominate. They act like planetary sunshades laid across the ocean. Scientists study them intensely because changes in their extent or thickness could alter regional and global temperature patterns. One of Earth's great climate regulators is not a violent storm, but a quiet blanket of low ocean cloud. The future of climate partly depends on clouds we still struggle to model. Climate models have become extraordinarily sophisticated, yet clouds remain one of their hardest challenges. The problem is scale. Global models must simulate the behavior of the whole planet, but many cloud processes happen on tiny scales, droplets forming, turbulence mixing dry and moist air, rising plumes interacting with cars, stable layers and particles affecting condensation. Those small processes shape the large cloud fields that influence Earth's energy balance. Scientists therefore use approximations informed by observations and theory, but the uncertainty does not vanish. That matters because future warming could depend strongly on how clouds change in response to a hotter world. If certain cooling cloud types shrink, warming could intensify. If others expand, they could offset some of the change. So part of Earth's climatic future is tied to forms in the sky that are still difficult to represent perfectly in equations. The planet's destiny is being influenced in part by clouds that remain frustratingly hard for computers to imitate. Other worlds have clouds too, but not like Earth's gentle water clouds. Once you look beyond Earth, the idea of a cloud becomes far stranger. Our planet has clouds made from water, tied to oceans, rain, snow, rivers, and life. Elsewhere, cloud chemistry follows different rules. On other worlds, substances we think of as corrosive, frigid, or utterly alien can condense and drift through the sky. That means the familiar softness of an Earth cloud is not a universal standard. It is one local version of a much broader planetary phenomenon. Across the solar system and beyond, atmospheres take whatever materials are available and turn them into visible layers, hazes, storms, and decks. A cloud on another world may carry no water at all. It may never produce rain a human would recognize. It may float above crushing pressure or in air colder than Antarctic winter by an unimaginable margin. Once you realize this, Earth's clouds begin to look both ordinary and precious, one beautiful expression of a far wider cosmic category. Venus has clouds made from droplets of sulfuric acid. The sky of Venus is one of the least welcoming cloudscapes imaginable. Instead of water droplets drifting through a breathable atmosphere, Venus is wrapped in thick layers of clouds composed largely of sulfuric acid. These clouds are bright enough to make the planet highly reflective, which is one reason Venus shines so strongly in our sky. But beneath that brightness lies a world of crushing pressure and extreme heat, where the surface is hot enough to melt lead. The acid clouds form in the upper atmosphere and help create a permanent shroud that hides the planet's surface from ordinary view. For a long time, they turned Venus into a mystery, because telescopes could see only the cloud tops. Even now, they remain part of what makes Venus both beautiful and hostile. When you see the morning star glowing near dawn, you are looking at sunlight reflected from a global envelope of acid cloud, brilliant to the eye and lethal in reality. Jupiter's clouds are stacked in bands of different chemicals. Jupiter's atmosphere is not organized like Earth's sky, with water clouds drifting above a solid surface. Instead, it contains immense layered cloud systems shaped by temperature, pressure, chemistry, and violent circulation. Different compounds condense at different depths, so the visible cloud tops are part of a deeper stratified structure. Ammonia is thought to form upper clouds, while ammonium hydrosulfide and water clouds likely exist deeper down. These layers are stretched into broad horizontal bands by the planet's rapid rotation and fierce jet streams, producing the striking striped appearance we see through telescopes. Between the bands, winds race at incredible speed, and giant storms can persist for years or centuries. The Great Red Spot is only the most famous example. What makes Jupiter's clouds so mesmerizing is their scale. They are not passing weather over landscapes. They are the visible skin of a colossal gas giant, arranged in belts, zones, and chemical layers across an entire world. Saturn's atmosphere can grow planet-wide storms beneath layered cloud decks. Saturn often looks calmer than Jupiter, with its pale gold tones and elegant rings, but its atmosphere can erupt into storms of astonishing scale. Roughly once in a Saturnian year at certain latitudes, the planet can produce enormous outbreaks, sometimes called great white spots. These storms grow so large that they can wrap around the entire planet, disturbing atmospheric patterns for months. They rise through layered cloud decks shaped by different chemicals and temperatures, and they unleash powerful convection in a world with no solid surface beneath the familiar cloud tops. Lightning has been detected in some of these tempests, and their disturbance can spread through the atmosphere like a planetary scar. Saturn's storms remind us that cloud systems do not need continents or oceans to become dramatic. They only need a deep atmosphere, internal heat, and the right conditions. On Saturn, a single storm can become a world-encircling event, unfolding beneath rings that seem serene above the chaos. Uranus and Neptune may host clouds of methane ice. Far from the Sun, where daylight is weak and temperatures plunge, the giant ice planets develop cloud systems from chemicals unfamiliar to everyday weather on Earth. Methane plays a major role in shaping their appearance. In the cold upper atmospheres of Uranus and Neptune, methane can condense into icy clouds. On Neptune in particular, bright methanized clouds are seen racing around the planet at high speed, tracing some of the fastest winds in the solar system. Uranus appears calmer much of the time, though it too can reveal storms and bright cloud features when conditions shift. What makes these clouds so striking is their setting. They drift in deep blue atmospheres, far from the warmth that powers Earth's water cycle. They belong to worlds tilted, dark, and remote, where weather still happens despite extreme cold and distance. Even near the outer reaches of the solar system, the atmosphere finds a way to turn gas into cloud. Titan has methane clouds that can bring rain to alien rivers. Saturn's moon Titan is one of the most Earth-like and unearthly places we know. It has weather, clouds, rain, rivers, and lakes, but the working fluid is largely methane and ethane rather than water. In Titan's frigid atmosphere, methane can evaporate, condense into clouds, and fall as rain. That rain can carve channels, feed river networks, and fill seas of liquid hydrocarbons near the poles. So Titan runs a weather cycle with a familiar structure but alien chemistry. It is like looking at Earth rewritten in another substance. The clouds there can gather in the lower atmosphere, drift across a hazy orange sky, and produce storms that reshape the surface below. For scientists, Titan is a treasure because it shows that cloud-driven landscapes do not require water if temperature and chemistry allow something else to play the same role. Somewhere beneath those methane clouds are rivers, shorelines, and rainstorms unlike anything on our own planet. Brown dwarfs may carry clouds of hot sand and metal. Brown dwarfs occupy the strange middle ground between the largest planets and the smallest stars. They are too massive to be ordinary planets, but not massive enough to sustain the full hydrogen fusion that powers stars like the Sun. Their atmospheres can therefore become laboratories of extreme cloud physics, at temperatures far hotter than Earth's weather but cooler than stellar interiors. Materials such as silicates and metals may condense into cloud particles. In other words, some of these objects may have clouds made from substances we think of as rock or metal vapor. These cloud layers can change, break apart, and rotate in and out of view, causing the brightness of the brown dwarf to vary over time. Astronomers can track those shifts and infer weather patterns on bodies many light years away. The result is mind-bending. A cloud does not have to be water or methane. In some cosmic atmospheres, even hot mineral grains can become part of the weather. Some exoplanets may have clouds of vaporized rock. On certain worlds orbiting extremely close to their stars, temperatures rise so high that familiar minerals can melt or vaporize. In such an environment, the atmosphere may contain substances that would be solid stone on Earth. If conditions are right, those vapors can condense into clouds composed of silicate particles or other rocky materials. This means some alien skies may not host fluffy white water clouds, but drifting mineral haze or even droplets and grains derived from rock itself. These worlds are often tidally locked, with permanent day and night sides, which can drive extreme winds and move material across the planet. In the hottest cases, rock vapor may rise on the day side and condense elsewhere, creating weather systems beyond ordinary imagination. The idea sounds like fantasy, yet it follows directly from temperature and chemistry. A cloud, at its core, is simply condensed matter in an atmosphere. On some exoplanets, the matter available happens to be the stuff of mountains. Studying clouds on other worlds helps us understand Earth's sky better. At first glance, alien clouds may seem too exotic to teach us much about our own weather. Yet comparison is one of science's great strengths. When researchers study how clouds form under different gravities, chemistries, temperatures, and sunlight levels, they are forced to identify the deepest principles that all atmospheres share. That helps refine our understanding of condensation, radiation, circulation, particle growth, and cloud feedbacks on Earth as well. Observing strange cloud systems on Venus, Titan, Jupiter, brown dwarfs, or distant exoplanets also reveals how special Earth's balance really is. It shows which parts of our sky are universal and which are rare. In this way, the study of alien weather throws Earth's own clouds into sharper focus. We learn more about our planet not by looking at it alone, but by placing it in a wider atmospheric family. Sometimes the best way to understand home is to see all the astonishing ways it might have been different. A cloud can seem ordinary, yet it connects oceans, weather, light, and life. That may be the most astonishing thing about them. They appear so often that it is easy to stop noticing them, yet every cloud is a meeting point of vast systems. Water lifted from ocean, lake, soil, or leaf becomes visible overhead. Air currents shape it into form. Some light gives it brightness, shadow, color, and sometimes a role in cooling or warming the planet. It may grow into rain that feeds forests, fields, rivers, or glaciers. It may drift over a city and soften the heat of afternoon. It may travel across continents carrying the memory of seas or deserts. Even the most familiar cloud is part of the planetary exchange linking surface and sky, physics and beauty, climate and daily life. That is why clouds reward attention so richly. They are never just decoration. They are one of the clearest signs that Earth is a connected living system, always moving water, energy, and possibility through the air above us. As we come to the end of our journey through the world of clouds, it is remarkable to think how much has been drifting above us all along. We began with their sheer scale, with clouds heavy enough to weigh more than 1 million pounds, and followed them into thunderheads that rise higher than mountains. We wandered through fog on the ground, glowing clouds near the edge of space, strange wave shapes, storm anvils, and skies lit green before hail. We traced clouds back to oceans, forests, deserts, cities, fire, and even distant volcanoes. And then, little by little, the sky widened even further, into climate, into other planets, into alien worlds where clouds may be made of acid, methane, or rock. It is lovely to remember that something so familiar can hold so much wonder. A cloud can be a veil of ice, a tower of storm, a silver ribbon at sunset, or a soft ceiling above the sea. It can drift in silence above a sleeping forest, gather over a mountain peak, or glow faintly while the last light leaves the earth below. Now, there is nothing more you need to hold on to. You can let all those skies drift slowly through your mind, one after another, and let them become softer and more distant. Let your breathing slow. Let your shoulders loosen. Let the day fall away, like light fading from the edge of a cloud at evening. And if you enjoyed this journey, you can leave a like, subscribe, or share a thought below. It helps other sleepy wanderers find their way here too. And if you happen to still be awake, there will be another video waiting for you on the screen. For now, just rest. Let your thoughts grow lighter. Let your mind float. Sleep well, and good night.